Ladies and gentlemen, welcome to the ultimate cosmic overhaul. Picture this. One day, you wake up and discover that our sun, the big friendly ball of incandescent gas that's been powering life on Earth for over 4.5 billion years, has been replaced overnight by Proxima Centauri, our nearest stellar neighbor, and a tiny, fiery red dwarf. How would Earth look? What about the rest of the planets? Could humanity adapt? Or would we all be packing our bags for a one-way trip to hypothermia? Grab your cosmic popcorn. We're about to embark on a wild scientific odyssey where the rules of the solar system are flipped upside down. Because why settle for the star we know and love when we can trade it for a smaller, temperamental neighbor prone to stellar tantrums? First, let's remind ourselves what we're losing when we boot our sun out of the sky. The sun is a G-type main sequence star, famously stable, shining around 380 trillion watts. Imagine having enough power to run billions of Earth-like civilizations all at once. In just 1 second, our sun releases more energy than humanity has used across all of recorded history. It's almost beyond comprehension, yet it's precisely what fuels our world with life-sustaining energy. It's massive, about 333,000 times the mass of Earth, and thanks to that hefty mass, it exerts a solid gravitational hold on the 8 planets, countless dwarf planets, asteroids, comets, dust, and the occasional lost spacecraft. The sun's magnetic field influences space weather throughout the solar system, guiding the orbits of everything around it, like a cosmic puppet master. From NASA's Parker Solar Probe to the ESA NASA Solar and Heliospheric Observatory, SOHO, we've spent decades studying our star's surface and its temperamental flares. Impressive, but usually not lethal for Earth, thanks to our planet's robust magnetosphere. Now, meet our replacement star, Proxima Centauri, commonly just called Proxima. If our sun is a shining celebrity, Proxima is that grumpy neighbor who keeps the lights down low and blasts out random bursts of energy at 3 a.m. for reasons no one fully understands. Type, M-type red dwarf star, distance from Earth, about 4.24 light years, practically next door in cosmic terms, mass roughly 12% that of the sun. So if our sun is a sumo wrestler, Proxima is more like a lean marathon runner. Luminosity. This is the kicker. Proxima emits only about 0.15% of the sun's luminosity in visible light. In other words, it's seriously dim. Special quirk. Proxima is known for robust stellar flares, a phenomenon that NASA's Chandra X-ray Observatory and ESA's XMM Newton have both studied. Every so often, it'll erupt with a powerful surge of ultraviolet and X-ray radiation. Fun, right? In 2016, a research team led by Guillem Anglada Escudé announced the discovery of a candidate planet, Proxima b, sitting in the star's so-called habitable zone. NASA's exoplanet catalog references this planet as an intriguing candidate for potential habitability. But the operative word is potential. With the star's intense flaring, that planet might need a magnetic field of steel to hang onto its atmosphere. So let's do the unthinkable. Snap our fingers and poof, our yellow sun is gone, and in its place stands Proxima. Same position, same orientation, but drastically different in every other way. Let's walk through the immediate fallout, shall we? With a star that's only about 12% as massive as the sun, the gravitational pull on Earth, still at 1 astronomical unit, about 93 million miles, plummets. Without that strong central anchor, the Earth will tend to drift outward. The technical term for this is we're on the express train to the deep freeze, because as soon as Earth starts coasting away from the star, it's going to receive even less of the already dim energy that Proxima provides. Other planets, Jupiter, Saturn, Uranus, and Neptune, could become cosmic vagabonds. Some might get ejected from the solar system altogether, turning them into rogue planets, wandering the galaxy alone. The entire architecture of the solar system would unravel like a poorly knitted sweater. Thanks for that, Proxima. Earth, our vibrant blue oasis, relies on a very particular balance of heat and light from the sun. By NASA's estimates, the sun's stable output is perfect for maintaining liquid water and supporting the complex ecosystems we cherish. Replace that bright star with a red dwarf that's thousands of times dimmer, and keep Earth at its present orbital distance, and you've got a recipe for an instant icebox. The heat budget is shattered. Even if Proxima emitted the same types of photons, just fewer of them, the raw energy output at 1 astronomical unit is minuscule. Within weeks, surface temperatures drop well below freezing. Most of the planet glazes over in ice. Ocean surfaces begin to freeze, starting at the poles and spreading inward. As Earth cools, more water vapor condenses out of the atmosphere, and greenhouse effects diminish drastically. This further amplifies the cooling in a runaway feedback loop. So let's just say your beach vacation in the Caribbean might get canceled for, forever. Most vegetation can't handle the drastically reduced sunlight. Photosynthesis grinds to a near halt. If the planet's drifting outward, each day we get less and less warmth. NASA's Goddard Institute for Space Studies has shown how sensitive climate is to solar input, and that's with small changes of 1 to 2%. Here, we're talking a drop in solar irradiance of over 99%. Plants, algae, crops, everything that depends on robust sunlight struggles to survive. Food chains collapse. Animal life follows. Extremophile microbes, deep-sea organisms near hydrothermal vents, and humanity, if we quickly develop nuclear fusion or advanced geothermal technology, might cling on for a time. But it's a dire scenario. The surface becomes something reminiscent of an Antarctic winter, but permanent and planet-wide. Of course, our minds immediately wonder, what if we could rearrange the solar system so Earth is at the right distance from Proxima for liquid water? Red dwarfs have teeny-tiny habitable zones located maybe a few million miles from the star instead of 93 million. Picture Earth diving in about 20 times closer than Mercury's present orbit around the Sun. At that extremely close distance, Earth would likely become tidally locked to Proxima over time. One side permanently faces the star, basking in eternal daylight, while the other side remains in perpetual night. This alone creates an extreme climate dichotomy: boiling deserts on the day side, sub-zero wastelands on the night side, unless strong atmospheric circulation can even things out. As a particularly feisty red dwarf, Proxima occasionally unleashes powerful flares loaded with UV and X-ray radiation. NASA's Chandra X-ray Observatory has recorded multiple flare events that would be catastrophic for unprotected planets. Earth's magnetosphere could buffer some of it, but repeated blasts might still chip away at our ozone layer, if not the entire atmosphere. If you're out on the day side, the star's redder wavelength means the lighting is reminiscent of permanent sunset. Plants, assuming some survive the transition, might evolve pigments better suited for red and infrared light. Or we'd have to engineer new photosynthetic pathways in a quest for agricultural survival. In other words, get used to the color red, it'll dominate everything. But let's not forget, Earth isn't alone out here. Our cosmic neighbors, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, are also caught in the aftermath. With Proxima's mass so low, each planet's orbit starts to wander. Already in the inner reaches, these planets might remain gravitationally bound, but they receive only a fraction of the energy they need to remain anything like they were. Both would cool down substantially. Mercury's surface, once baked by the sun, would freeze. Venus's dense CO2 atmosphere might keep things warmer for a bit longer, but eventually, even that wouldn't sustain the heat indefinitely. Currently, at one point, 5 astronomical units, Mars can barely muster enough heat for the occasional mild day in the summertime. Under Proxima's rule, it becomes an even more frigid desert. The dream of Martian colonies would only be feasible underground or with domed habitats reliant on nuclear or geothermal energy. These gas and ice giants already rely partly on internal heat generated by gravitational contraction, especially Jupiter and Saturn. But they still count on the sun's warmth for atmospheric dynamics. With Proxima's meager luminosity, their cloud tops become colder, and their iconic storms, like Jupiter's Great Red Spot, could diminish in intensity. Over very long timescales, these giants might roam off if the gravitational interplay in the system turns chaotic. Once the shining brilliance of the sun is replaced by this dim, ruddy star, the outer Kuiper belt and Oort cloud might barely notice the difference, except that the gravitational weakening could fling them in every which direction. Some might careen inward, potentially leading to a spike in cometary visits to the inner solar system. Others might be ejected, journeying across interstellar space like cosmic refugees. One of the biggest challenges in red dwarf systems is dealing with the star's temper. Proxima, as documented by NASA's Transiting Exoplanet Survey satellite, TESS, and the European Southern Observatory's telescopes in Chile, can flare with little warning. These flares aren't just pretty lights. They're blasts of charged particles and dangerous electromagnetic radiation that could fry unprotected electronics, degrade planetary atmospheres, and wreak havoc on satellites and communication networks. A big flare could spike the UV or X-ray dose on a planet by orders of magnitude. If Earth is close enough to be in Proxima's meager habitable zone, that's a barrage of harmful radiation capable of causing DNA damage to living organisms. Over millennia, repeated blasts can effectively peel away an atmosphere lacking a strong magnetosphere. If there's a lesson to be learned, it's that if you're going to orbit a red dwarf, you'd better bring a robust planetary force field. Now, humans are resourceful critters. We've overcome ice ages, scorching deserts, and even 2020. If we have enough advanced warning, let's pretend we were in on the plan to swap the sun. We might scramble to prepare. Without reliable sunlight, solar power is out, so you'd need to harness the Earth's internal heat or rely on nuclear power. NASA's Glenn Research Center has studied small nuclear reactors for space colonies. We'd be applying that knowledge right here on Earth. Greenhouses would have to be sealed with LED-based grow lights powered by nuclear or geothermal sources. Hydroponics and aeroponics become the lifeblood of humanity's food supply. High-energy radiation? No problem. Just add thick layers of water, rock, or specialized materials that can absorb cosmic rays. Underground habitats might be an attractive option, turning subterranean city life into the new norm. Our reliance on sunlight permeates everything: agriculture, ecosystems, day-night cycles, mental health. We'd be forced to adapt to artificially lit environments, carefully rationing energy, and dealing with a drastically changed climate. Would it be pleasant? Probably not. Could we do it? Possibly, especially if we're prepared for some serious 24/7 red strobe lights from our new star. Red dwarfs are known for their longevity. They can live for trillions of years, whereas our sun, by NASA's standard models, has a main sequence lifetime of about 10 billion years. In theory, if Earth manages to survive the gravitational chaos, the flares, and the freeze, it could remain in orbit around Proxima for an extraordinarily long time. However, the constant barrage of stellar tantrums might wear down any planet's atmosphere over the eons, and the initial rearrangement of orbits, plus the dramatic cooling phases, would likely exterminate most life in short order. The odds of advanced life re-evolving from scratch under these harsh conditions are, at best, questionable. But imagine a hypothetical scenario in which Earth is teleported to just the right distance, a stable orbit within Proxima's habitable ring, shielded by a powerful magnetic field. Over billions of years, new forms of life might adapt to the red-hued environment and intense flares. Evolution could yield hardy, radiation-resistant organisms that see daylight under a permanent crimson sky. It's the stuff of science fiction, but as we push the boundaries of exoplanet research, like NASA's ongoing exoplanet surveys, ESA's Gaia mission, and the James Webb Space Telescope's exoplanet atmosphere analyses, we start to realize these exotic conditions might not be so far-fetched on planets orbiting real red dwarfs. As we explore more exoplanets and red dwarf systems such as those found by NASA's Kepler, TESS, and studied by Hubble or the James Webb Space Telescope, we inch closer to understanding whether life can thrive under a dimmer, much more volatile star. Maybe somewhere out there, on a planet bathed in red light, bizarre creatures have evolved to withstand epic flare storms. Or maybe they built underground cities ages ago to ride out the cosmic chaos. For now, here on Earth, let's be grateful for our bright, relatively calm sun. and hope that no cosmic real estate agent comes along with bright ideas about switching us to a smaller, more temperamental star. Because while Proxima might outlive the Sun by trillions of years, it's definitely not the easiest star to cozy up to. Thank you for joining us on this cosmic escapade. If you've enjoyed pondering the fate of Earth under the mischievous glow of Proxima, remember this: science thrives on curiosity, and hypothetical scenarios, no matter how wild, expand our imaginative horizons. Please consider subscribing, sharing, and hitting that like button. And don't forget to leave your own what-if ideas in the comments below. So keep looking up at the sky, keep exploring the worlds beyond, and rest easy in the knowledge that tonight, when the sun sets, it'll still be the same friendly star we've always known, at least for the next 5 billion years or so.